factorization and its principle. Of course, on Monday, I walk you through some matrix factorization technique. I remember LU decomposition, Koleski, um, non-negative factorization matrix, uh, single value decomposition, and so on like that. And all of that actually centered on decomposing original matrix into smaller matrices in such a way that when we combine the smaller matrices, we're only going to have an approximate original matrix. And because there's always going to be a gap between the original matrix and the product of the smaller matrices, okay, and that is the reason why we normally want to optimize, or we don't have optimization problem where we want to minimize the sum of square distance. Okay, so and that's actually so when you take a look at matrix factorization, of course, has a very wide range of application in statistics, machine work, and the scientific community in general. Okay, you want to talk about image processing, you want to talk about face recognition, you want to talk about you know what we call maybe selecting genes, uh, most important genes in gene expression data and so on like that. Okay, now one of these factorization technique is also a PCA. PCA is also a factorization, matrix factorization technique. I remember on Monday, I actually walk you through how we can use PCA and non-negative matrix factorization, in image compression. Okay, and of course, the non-negative factorization, matrix factorization, is so special because you're splitting matrices into in original matrix into two simpler matrices, and you actually impose a restriction that the two have to be non-negative. And because of the non-negativity in the non-negative matrix factorization, okay, that is very, very useful in statistics and machine learning world, because if you're talking about image processing where we work with pieces, pieces need to be non-negative. It's always non-negative. Talking about gene expression data and so on like that, okay, requires that we should have a non-negative. Okay. Okay, so coming from that, I'm gonna go into a potential issue with PCA. The other time, when I walk you through principal component analysis, the idea, our intention with the principal component analysis is just for us to reduce the dimensionality in a data set. We work with large volume of data set with so many features, and there's possibility, of course, apart from the fact that we have so many features that induce complexity, and that is a dimensional problem. And how do we reduce it in such a way that we're not going to lose significant information? Okay, just like I gave you an example in image compression, where we trying to compress our image. Why are we compressing our image? Because the more dimension in an image, the more storage facility that you need. I'm going to say that again. The more dimension in an image, the more storage facility you need. Getting that more fast, storage facility may be costly, and that is why we got intention of reducing the dimensionality of image in such a way that we're still going to guarantee the quality. Okay, we're still going to guarantee the quality. Okay, even though we're going to lose some information. But one thing with the principal component analysis, after generating new principal components, each principal component is still a function of the original variables, original features. Okay, I'm going to say that again. Each principal component is still a linear combination of the original set of features. And because of that, because we still have the original set of features, that is going to make it not interpretable. So what I'm trying to pass across right now, principal component analysis as interpretability issue, because of the fact that we're able to retain all the original features. But what is the benefit of the conventional principal component analysis? The benefit is it was able to retain maximum information, and that was why we call it variance maximization. That is the benefit. But what is the sacrifice? Then the sacrifice is interpretability, and that is a potential issue with PCA. Okay, and that is the reason why we need to consider variance of PCA. Statistics is so interesting. Machine learning world is so interesting. Mathematical world is interesting because if there's a problem with one approach, we normally have a way. We normally have a way out. Okay, so like I said, this is what we observe. I said, the key observation is that the SPARSE loading make it easier. So what we want to do now is, can we have a way to incorporate sparsity into what I call sparsity constraint into principal component architecture? And what that very sparsity constraint is going to do is instead of us to retain all the original features, the sparsity constraint will shrink some omnipotent feature to the coefficient to 0. What do I mean by the coefficient? I mean loadings. Okay, loadings. Okay, to 0. So that some features will be completely, some features will be eliminated. That's what we call sparsity. Okay, that's what we call sparsity. Okay, so I said PCA achieve optimality in average sense, maximum variance, smallest approximation error, but it may sacrifice the interpretability. And for us to have some sense of interpretability, that we need to incorporate sparsity constraints. Does that make sense to everyone? We're actually sparsing right now. We want to sparse because we wanted to shrink coefficient of the original features to sum to 0. Because the reason why it is not interpretable in the first place, because we still retain all the original features. Okay? Now, because of that, I want to introduce to sparse PCA. I used to tell you, statistics, okay, data science, machine learning world is like a story that goes on and on and on. So, like I said, right now, okay, like I said right now, I want to introduce us to sparse PCA. And I'm actually going to say we find ourselves doing sparse PCA because of the limitation we experience because of potential issue with the PCA. And what is the issue with the PCA? Interpretability is the issue. And that is why we actually want to sparse. We want to introduce a sparsity constraint into the architecture. Okay, so And that was why I said, can we introduce the sparsity in PC loadings such that we get better interpretability? Statisticians, machine learning experts, we think a lot. Okay, we think a lot. So that is, don't forget the PC loading means the principal component loadings, which are the weight, which are the contribution of original feature to the principal component. Is there a way we can shrink some of that to zero? Shrinking some of less important features to zero, we completely eliminate some features. And the benefit from that is actually interpretability. But that's also come with a penalty too, because the sparse PCA does not really guarantee maximum information. The conventional PCA, okay, guarantee maximum information, maximum variance. But the conventional PCA is not that interpretable. But the sparse PCA right now, okay, we're gonna shrink some coefficient, some features to zero after incorporating sparsity or constraint. Okay, that will be more interpretable, but the maximum variance is not guaranteed. But we got a way to do. And that was why I said, no, there's no way you can still keep all the optimality of PCA. Because the maximum variance is not guaranteed. And then also increase interpretability. Oh my God, there is no free lunch. You see that? No free lunch. Okay. But what we normally want to do, we acknowledge this kind of problem that we cannot eat your cake and have it. There's no free lunch. Is there a way we can balance? And that's why we need balancing. The balancing is going to be, okay, is there a way I can retain reasonable maximum information, and not only that, I can also benefit for interpretability. And that's why the nature of the sparsity constraint you are introducing matter. Okay. And that's why I said sparse PCA is just a way to achieve a different trade-off. We sacrifice a bit optimality and get a better interpretability. So whether this is a wise choice depends on your application. It depends on your application. Okay? I'm actually going to work it out. This actually started in 2006 with Zuesti and Tishirani, 2006. We implemented that in our package that we call Elastic Net. But let me tell you this. Similar to what we've done in NMF, because we haven't done FA, we're still going to do FA. FA means factorial analysis. We're still going to do that. But we've done NMF, that we call non-negative matrix factorization. I said there are many different algorithms to find sparse PCA. Okay? And they may give different results. And why do we have different algorithms, to find a sparse PCA? Because the constraints that we're going to introduce, we got different kind of constraints, which I'm actually going to walk you through. But I said something here. It does not use the maximum variance motivation for PCA. Instead, it finds the sparse vector to achieve small approximation error. Now, I think I will quickly do this before coming to this picture. I wanted to see this, and I'm going to go back to the picture. Now, You know, I told you the other time, we got different kind of constraints that can be incorporated into PCA structure to make it sparse. Number one constraint that we call is regularization technique is called L1 penalty. L1 is called lasso. Has anybody heard about lasso? Lasso? Lasso regression? Okay, you're still going to do lasso in 4052. You've heard about lasso, right? Okay. Now, we have L1 penalty that we call lasso. We have L2 penalty that we call reach. We've applied that in statistics, and let me tell you this. The lasso penalty, if you are using lasso penalty, if you incorporate that into the PCA model. When I say lasso penalty, let me show you this. Give me 1 second. I'm gonna make use of this guy now. Okay, take a look at this guy here. Okay, you can see something one, right? L1. Okay. Now that very V1, that L1 is what we call lasso penalty. And what lasso penalty, what it's going to do is to shrink some coefficient to zero. Some coefficients, some features that are less important. It's going to shrink them to zero. But let me tell you this. The potential issue with lasso penalty is that it's actually going to be unstable if features are highly correlated. I'm going to say that again. If features, now I'm going to say this now. Without this guy here. Okay, if I only have, if I only, if I, oh, sorry, if I only, if I only have, please pay, I need you to pay attention. If I only have this, then it means I'm only using L1 penalty, lasso penalty. Okay, what is the first one? Okay, the X and V. The X is your original matrix. That's what I put here. Take a look at that. X is the data matrix. Your V's are the loadings. Okay, do you see that now? So the V1 is what we call L1 norm that we call lasso penalty. Then the V2 square is the L2 norm that we call reach penalty, reach time. But what I'm trying to say, if you only have this, then it means you've only incorporated L1 penalty lasso. But you know the benefit of that? It will successfully shrink the loadings with less important features to zero. But do you know the disadvantage of just using lasso? The disadvantage of using lasso is that it's going to be unstable when features are highly correlated. Okay? And that is the reason why we consider L2, which is the range. So if I consider this guy with this guy, oh sorry, with this guy, okay, without this guy, I'm considering reach. Okay, now when I'm considering reach is not going to shrink the coefficient to zero, but reach we consider including or excluding features that are correlated. Look at that. And you now see that L1 penalty has limitation, L2 penalty has limitation, and that is the reason why is there a way we can combine the two, and that is what we call elastic net. Elastic net combine both L1 penalty and L2 penalty. And the turning parameter is alpha. You know what I mean by turning parameter? That turning parameter is going to enable you to switch from lasso to reach. But let me tell you this. When alpha equal to 0, can somebody tell me what am I going to have on the board? When I plug in alpha to be 0, can somebody tell me? Am I going to have reach or lasso when alpha equal to 0? I'm actually going to have reach, which means when the turning parameter equal to 0, then you have a reach penalty. When the turning parameter alpha equal to 1, then you have lasso. But you know, the proposal is alpha is going to lie between 0 and 1. So if the turning parameter lie between 0 and 1, then the elastic net will actually, balance, it create a balance which will switch from lasso to reach, like that. Does that make sense? So this is going to be more beneficial. And this is the reason why we use elastic nets, okay, to sparse PCA. Now, this is the regression form of it. This is elastic regression. If you take a look at this in statistics, that's how I call it elastic net regression. Maybe you want to perform linear regression and you got so many features. And in order for you to avoid overfitting, overparameterization, what do we mean by overfitting? Overfitting actually means you got a lot of features in the model and they're going to create problem. Your model will perform great on training, but will perform poorly on the test data. And that's not good at all. And that's why we normally incorporate either L1 or L2 or the combination of the two that we call elastic net. If you see why that, when you take a look at this alone, when you take a look at this, if you take a look at this, that is the sum of square error in the conventional linear regression. That's the sum of square error that you want to minimize. But if there's so many features, then we normally add in penalties, whether L1 or L2, or we could mix both. Okay, so I'm actually going to say there are 3 major benefits that actually come with sparse PCA. Okay, major benefit that come with using formulating sparse PCA via elastic net. Number 1 is sparsity, and which one is going to do the job of sparsity? L1 penalty will do the job of sparsity. Okay, which means L1 penalty will shrink the loadings or the coefficient of less important features to 0. So number 1 benefit is sparsity, and L1 is going to do that. Number 2 benefit is grouping effect. Grouping effect. And you know what is going to do that? That will be L2. We do that. L2 now. The ridge. We do that. Okay. The grouping effect is that one is going to decide whether to include or exclude correlated features that L1 is going to struggle with. And number 3 benefit is flexibility. The flexibility here is that with elastic net, you are able to create a balancing between the 2 penalties. And that is why your turning parameter alpha is in the equation. Your turning parameter alpha is going to lie between 0 and 1. Does that make sense to everyone? Any question? You're good, right? Okay. Now you know what I want to do now. I want to go into application. Very useful in bioinformatics, where you got thousands of genes and you only want to identify, okay, those genes that contribute to the variance in the gene expression data. Also has application in finance. In finance, you could have so many features that will even be more than the number of observations, the number of time series that are point. And of course, there's going to be problem of high dimensionality. And of course, using this will be able to reduce that, while you'll be able to maintain interpretability, because we need interpretability properly. Interpretability is what is making statistical model to be attractive to everyone in the world. Whatever we do in statistics are very, very interpretable. Okay? Now, I want to go into this now, and I need you to pay attention. Okay? I need you to pay attention. Please pay attention to this example, surveillance video. Okay? You know, there's something that we call sparse PCA, right? But do you know that we can also have a way to partition our matrix into two, but this time around, we've been having decomposing matrices into the products of smaller matrices, right? But at times, we're actually going to have this. I'm going to write something now before explaining what you see in the picture, so that you can have a better understanding. If I have a matrix X and I want to partition that, okay, into what I'm actually going to call L plus S. The one we've been having is partitioning original matrix or decomposing original matrix into the products, right? But we also have situation where we can partition into, two matrices that can be added together. And you know what? This is what we call low rank, sparse plus low rank model. Now I needed to see this. You see what I write? Low rank plus sparse. Low rank plus sparse. Now, which means original image, we want to break it down into two matrices. One is going to represent low rank. The second one is going to represent sparse. Adding them together will give us original S. Now I'm going to use example in surveillance video. If you go to public sector, most of the public buildings have surveillance video. I need you to pay attention to the surveillance video. Oh my God, take a look at this guy here. That is the original surveillance picture. Can you see that? That's like an X. This is like a matrix X. Okay? Now we want to break it down, because in this original matrix, you're actually going to see a static background. You're also going to see some dynamic movements, right? That's a typical of a surveillance video. But can we have a way to partition the original surveillance video into low rank, okay, into low rank approximation plus sparse? What do we have? Now I need to take a look at this. What do we have in a low rank now? In a low rank, okay, what you see in the low rank is only static background, okay, no movement. But if you take a look at the sparse, okay, the sparse will concentrate on dynamic movement. It's going to focus on people. It's going to focus on real event. It's going to focus on noise. It's going to focus on anomalies. Take a look at that. You see the low rank. So the idea behind low rank plus sparse model is to separate dynamic objects from static background. So that we're going to have the first picture in the low rank is going to give us static background. The second picture is actually going to give us a real event, dynamic movement, and that is the reason why the second part, the sparse, is really focusing on the movement, the human beings. Okay, so I just wanted to take notes of that. Now I want to move. Okay, this week I told my TA to relax. You didn't have lab, right? So, and I asked him to send you information, just relax, for the week. Next week, of course, assignment and lab are going to return. So what you're going to do in the lab next week, of course, you're going to do sparse PCA, non-negative factorization in R, how we, whatever we did during this week is what is going to be the focus in the lab next week. I needed to take a look at this. I want to perform a sparse PCA in R, okay? And I need to load some packages because the constraints, the sparsity constraint I'm actually going to introduce is elastic net. Don't forget, elastic net is the one that misses both penalty, the L1 and the L2. And also having my data set right now, and let's see results. I needed to take a look at this. You got 4 principal components, but pay attention, something is happening. In principal component 1, 2, 3, 4, you can see that. Take a look at this. What do you see? Zeros. Can you see that? Zeros. Initially, with the conventional principal component, you are not likely going to see all those zeros. Do you see that? Do you see all this one? Zeros. You know what has happened? The L1 penalty that I call the lasso has shrink or less important feature within a principal component to 0. Okay, which is going to make it more interpretable. You see that? We lost some features within a principal component. Take a look at all of that. This is going to make it more interpretable. Okay, this is going to make it more interpretable, but this is also going to make it not to get, there's no guarantee of maximum information. Does that make sense? Okay. Okay, so I said in some sense, any method that seeks for intrinsic structure in matrices can be seen as factorization. Okay, so there can be other interesting structural assumption depending on the application. So e.g., I said, how about a non-negative and sparse factorization? And I said this idea will also be used in hardly missing entries. Now, let me tell you this. We want to go into something else. We're done with sparse PCA. Is there anyone who want to ask a question about sparse PCA? Okay, if you look at the syllabus, because we are now getting into, I think we are more than maybe 40% or very close to 40% completion of the entire semester. I'm actually going to release information about group projects. Okay? Because why is it that I've not released that information about group projects earlier? Because you haven't done anything. You have nothing to think about. Like, you have nothing to write about. So watch out this week. You're going to receive information about group project. But before you think about group project, I need you to first understand everything that we've done. Now, I want to go into something else. What if in a situation, I want to welcome you to missing data, matrix completion, and recommend their systems. Let me tell you this. At times, when we are working with matrix, we could have some missing data. Okay. And when we have some missing data, can we have a way to estimate them using the idea of a matrix of factorization or algorithm that we have around. Okay. And of course, there was a competition organized by Netflix. Okay. Where the Netflix asks customer to rate some movies, and customers only rated the movies they watch. They did not rate the movie they did not watch. And because of that, that creates a problem of missing data. But you know what? Netflix really wants to have a way to estimate the missing data point for them to be able to recommend their movies to customers, to the outside world. But you know what happened? The internal algorithm they try to use an algorithm within Netflix, and they they were able to do that. They recorded root mean square error of 0.9, I think like 575, and they wanted researchers or group of researchers that will have a 10% reduction in the root mean square error. And they put a price of $1 million. That's a lot, right? I'm actually still waiting. I want to see whether they still have the competition on. So we got a lot of people, researchers that submitted, and somebody won the prize eventually because it was able to drastically reduce the root mean square error. I want to welcome you to matrix completion, where we could have missing values. I said data matrix may have some missing entries, and that can be a problem moving forward, just like what I said. Many of our modeling procedure require complete data. Because with missing data, there's going to be an issue. What are we going to do? Okay, we need missing data imputation. Okay, and you know what? Sometimes imputation can be treated as a prediction problem. Why prediction problem? Because we want to predict those values that are missing. That's why it's a prediction problem, which is very, very useful in recommender systems like Netflix, Amazon, and so on like that. So matrix completion can be seen as both of a supervised or a supervised problem, depending on your goal. So what we're going to do here is to use the idea of matrix completion. That's why I'm welcoming you into matrix completion. Okay, we assume values are missing completely at random. When values are missing completely at random, the missingness is not informative. There's no any information than to just look for a way to predict the missing values. Now, but let me tell you this. There have been some approaches that was adopted whenever data points are missing. You know, at times they're going to say, which is called the simplest approach, where we're going to replace missing value for a variable by the mean of the non-missing entries. You know, for instance, you have a particular variable, let's say height, and one particular person does not provide information about his height, and you want to predict that. Okay, what we normally do the traditional way, naive way, is to find the mean of others and use it to replace it. Okay, but you know what? That approach, we ignore the correlation. So the drawback, okay, it ignores the correlation among variables. Okay, and we may need to exploit this correlation for imputation, and that is the reason why we need a special method doing this. Okay, now we assume values are completely missing at random. You know, missingness is not informative. Okay, now this is the application I was trying to tell you the other time in a recommender system, where they have matrix of users and they have them to rate movies. I need you to take a look at the board. Let's say we got Tom, Jerry, Danny, Sarah, and Edwin. And then look at those movies. Tom only watched the second movie and the third movie, and he only provided rating for them. Tom doesn't watch the first movie and the fourth movie and the fifth movie. Because of that, those rating are missing. Does that make sense? Now, the same thing, if you look at Jerry, now this is a sparse matrix. We needed to have a way to predict the values that are missing. Okay. So like I said, Netflix actually puts a price. Okay. They have a data of 480,000 users, 18,000 movies. There's so many. I'm just showing you movie 1 to 4. There's so many of them. 18,000 movies, 100 million ratings, and the rating is on 1 to 5. But you know what? 99% of ratings are missing. Look at that. That's a lot. And what is the goal? They actually put there's a reward incentive in focus to encourage those who are actually going to do a great job. But you know what? The algorithm available in Netflix, they've already used that. They call that sign match, and they have root mean square error of 0.95 something, and they wanted a reduction. They're looking for somebody who was going to reduce that. But a team finally won the award because they were able to drastically reduce the root mean square error. And I'm also waiting for another opportunity in the future where some of us, we're going to participate and further reduce. Now, let me tell you this. For you to be able to understand matrix completion on how to estimate, how to make a prediction for missing values, I think we need to first understand matrix approximation by PCA, which will provide some knowledge. I got an X, okay, a data matrix X, and I partition into A and B. Don't forget, A is going to contain principal component, K principal component, and B is going to contain the corresponding loadings. And of course, if I multiply the smaller matrices together, there's always going to be a gap when I compare with the original matrix. And what you are seeing right now is how do we minimize the sum of square distance. Okay? Now, minimizing sum of square distance. Okay, so this is another way to put that. And we can go by way of singular value decomposition. By way of singular value decomposition is actually, I wanted us to use a low rank approximation, just like what I said on Monday. Because the idea of this will be used in matrix completion, in predicting missing values in matrix. And that's why we're actually revising this with you. When I have a singular value decomposition, the number of singular values correspond to the numbers of rank. A matrix that have a full rank actually means it has a perfect complete information. We don't want a perfect complete information because of storage issue. And that is the reason why at times we want to have a kind of reduction in rank, and in such a way that the number of singular values we're going to choose at the end of the day, we're still going to retain the information. So this idea is going to be used. Okay, that's exactly what I'm trying to say now. So matrix approximation by PCA, I said, what to do if matrix has missing elements? What do we need to do? Okay, of course, we're going to focus only on the observed entries. Okay, and when we focus on the observed entries, can we look at the pattern in the observed entries using some available algorithm that has to do with a low rank approximation for us to be able to have it completed? And that's the reason why on Friday, the focus is going to be on matrix completion. How do we predict entries in matrix via principal components? This is where I'm going to stop today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.